Last video we took a look at the modes of heat transfer, and here we'll start to think a little bit about what happens as we transfer heat in or out of an ideal gas. So the first process I'll take a look at is an isochoric, or it's also known as an isovolumetric process. This is one where the volume remains a constant. So you can just imagine that you have a container, you light up a flame underneath it, and the gas gets hotter. If we were to measure the pressure on it, we would see that the pressure would increase. So in chemistry, you would have looked at this and said, okay, since it's an isovolumetric process, Gay-Lussac's law is at play. But a good way to be able to remember it is to use scaling. So what you can do is you can write down the ideal gas law, PV equals nRT. And then for anything that stays the same, you don't do anything to the letter. And for anything that changes, we'll put subscripts down. So here this will be a P final, and that will be a T final. The ideal gas constant and the number of moles won't change, and in an isochoric process, the volume doesn't change either. And then we'll divide that by the same thing, except in the initial situation. You can cancel out things that stayed the same to be left with Gay-Lussac's law. So in an isochoric process, the ratio of the pressures goes as the ratio of the temperatures before and after. Now, a way that physicists will represent this process is to make a thing called a PV diagram. And it's not a graph, it's a diagram. And what you do is you draw a dot at your initial condition and a dot at your final condition, let's say. And then you draw a line that connects these with an arrow showing the directionality. So here, because the volume never changed, this isochoric heating is going to look like a vertical line pointed up. If we're in isochoric cooling, if say we stuck the whole thing in an ice water bath to take heat out, that would be an arrow pointing down. Now, another process we can take a look at would be an isobaric process. And if we break the Greek roots apart in this, iso means the same, baric, bar as in pressure, barometer, that kind of thing. In isobaric process, the pressure is a constant. So we can do exactly the same. So here what you can just imagine doing is, say, having a piston. So here's the cylinder, there's the piston head free to float, and you got some gas in here. So the pressure is going to be atmospheric pressure plus the weight of the piston head divided by the area. Now, if I introduce a flame, we will have an isobaric expansion because the thermal energy of the gas will increase. So it'll increase the pressure of the gas, so it'll want to expand. Well, as it expands, that's taking the pressure of the gas will decrease, will be decreasing as it's expanding, and it's constantly maintaining a constant pressure. It's constantly pushing the cylinder up. Now these fluctuations in pressure are minuscule, and so you can basically say that's a constant. So the net result is that the volume got bigger. So again, we can scale the ideal gas law for this. PV equals nRT. And we'll put subscripts on the things that change. In this case, it'll be the volume and the temperature. And then we'll divide by the initial condition, cancel common factors. And what we get is the ratio of the volumes goes as the ratio of the temperatures. This is Charles' law. Now, the PV diagram for an isobaric process is going to look like a horizontal line. So if it's an isobaric expansion, the line will be pointed to the right because the volume is increasing. If it's an isobaric compression, the line will be pointed to the left because the volume is decreasing. And now let's go ahead and look at an isothermal process. Iso the same, thermal the same temperature. So here the temperature is a constant. So here what you could have is a cylinder. We'll put our piston head on here. And then you put the whole thing into some sort of constant temperature surroundings, like let's say you have an ice water bath. So here's some ice, some water, and then we've got some ice cubes that are floating in it to ensure a constant temperature, as an example. If you were to push down on this, the volume would decrease, and for you to push down on it, you'd have to have done work, so you would have increased the average thermal energy of the particles, so the pressure would increase. So let's follow that through from the ideal gas law. So we can again write PV equals nRT. Here the temperature is a constant, so we're just going to say final. And then we do the same thing for the initial state. And we get P final V final equals P initial V initial, which is Boyle's law. And a PV diagram for this well, let's say it was an isothermal expansion. Since the pressure and the product of pressure and volume are constant, if pressure goes up, volume has to go down. So they're going to go as reciprocals of each other. So here the pressure will be proportional to 1 over the volume. And where on the curve you are is indicative of temperature. So if you're, say, here, this isotherm, we call the curve, would represent a lower temperature than, say, this isotherm here. These are all supposed to be going as 1 over V. And the temperature here is somewhere in between. So the closer to the origin the isotherm hangs out, the colder the substance. Alrighty. And in the next series of videos, we'll start to take a look at how much heat we transfer in and out in these processes and start to think about how much work we can get in and out. Catch you on the flip side.